think you're still on mute.
I'll try again. Our next speaker is Karyn McLellan from Mount Saint Vincent University in Halifax, who speaks on Fibonacci numbers. Please.
Great. Thank you for the opportunity to speak. So I'm going to be talking on problem on generating sets containing Fibonacci numbers. And I should mention that this is joint work with Danielle Cox. Okay. There, wasn't changing, there we go. So I've split this talk up into 3 parts. The first, we're gonna look at a problem that was introduced and look at some patterns that will help us in solving the problem. Then we're gonna generate a formula that will help us to do that. In the third part, we'll come back and re-examine the problem. So the problem in question was posed at the 16th International Fibonacci Conference in 2014 by Clark Kimberling. So we're going to start with the set S, and it's a set of integers, and it's generated by the following rules. So we start with S containing only the element 1, and then for any element X in S, we assume that 2 times X is in S, and 1 minus X is also in S. So the idea is that the set S grows in generations. So we can look at these generations starting with 1, and then say if we apply these 2 operations, what new elements get added to this set, and so on. So by only adding new elements every time, we get disjoint sets. So the question is to prove or disprove that each generation contains at least 1 Fibonacci number or its negative. So this appeared to be kind of a curious property when we start generating these sets. So we'll call G sub I generation I, and we'll call I itself the generation index. So as I mentioned, we'll note that these sets GI are pairwise disjoint because they consist only of the new elements that we're adding to S at any given time. So we kind of restructured this problem a little bit. Instead of starting at 1, we could analogously start at 0. And we'll take sort of a closer look at the first few generations here. So instead of starting with 1, we're going to start with 0. So remember, we can double it or do 1 minus any element in the set. So of course, if we do 1 minus 0, we get 1, and doubling it gives us nothing new. So we have only element 1 in G1. We double 1, of course, we get 2. But if we do 1 minus 1, that takes us back to an element we've already seen, so we don't add it in. So you can see sort of how this goes. 2 doubling gives us 4, 1 minus 2 gives us -1. In the next generation, we can double both -1 and 4 to get -2 and 8. 1 minus 4 gives us -3, but 1 minus -1 gets us back to 2, so we're not adding that element. So you can see the first several generations here. In bold, you can kind of see the bolded numbers. Those are either Fibonacci numbers or the negatives. So it seems like as far as we were sort of able to calculate this by hand, and even with some computation, this pattern seemed to hold. So far we can see that this pattern is holding. So it makes sense to think of this set S in terms of a binary tree, right? So we have 2 operations that we can apply at any stage to any number. And we're going to think of the right child as being the doubling operation, the left child as being the 1 minus operation. So we'll come back to the tree in a minute, but we're going to discuss some of the structure. There's some really interesting structure in this tree. So to start, a couple of straightforward results is that for even elements of any generation GI, and we said that those are the right children, they come from doubling all the terms of the previous generation, which is pretty obvious. And just to understand the structure, we also have that all of the odd elements of any given row, which are highlighted here, 3 and -7, they come from 2 generations back if we double and then do 1 minus. So the combination of those 2 operations. So basically in any given row, if we go 1 generation back, we're doubling all of the elements. And if we go 2 generations back, we're doing 1 minus the double of all the elements. So we can see sort of recursively how this tree is growing based on those 2 operations. Notice that the tree doesn't have any patterns where we go left then left, because of course the 1 minus X operation would get us back to where we started if we applied it twice in a row. So you'll notice that all the right children have 2 children and all the left children only have a right child in the tree. So it's an interesting structure that's appeared in other places as well, not just specific to this tree. So of course, the first obvious result then is, you may have noticed if I skip back and look at the set of generations, if you're into Fibonacci numbers, maybe this would jump out at you right away, that the sizes of these generations are all Fibonacci numbers. And of course, that follows immediately from what we said about each row coming from the previous row and all terms in the row before that. So it's a simple induction to see that the sizes of all these generations are Fibonacci numbers. It's also interesting to note that all integers also belong to the set S. So we can think of this set S generated by these rules as partitioning the set of integers, positive and negative integers, into our sets GI. And it's a simple proof. We can basically just use a straightforward contradiction. If we start by assuming some integer k is not in the set, we can sort of trace a set of operations backwards through the tree such that they decrease, the numbers decrease in absolute value, and we can make our way all the way back to the root given any k. So by contradiction, we can prove that the set S does indeed contain all integers. So we want to get sort of a better idea of what's going on in the tree. Remember, we're interested in Fibonacci numbers and where they occur, but we'll start by thinking about, okay, where do just any old integers occur? So if we're given some integer k, and I'm going to run through them, 0, you can see 1, -1, 2, -2, 3, -3. So each integer followed by its negative. Next to it in the column I is the generation index. So where that integer occurs in the tree. So I've bolded that sequence. You can read it down column-wise, and I've kind of grouped it in rows of 4 for a reason we'll see soon. So of course, when we got this bolded sequence, the first thing we did was stick it in OEIS, and it wasn't there. It is now, but it wasn't there then. So what can we say about this sequence? So we're going to uncover some patterns that are found in the sequence in this table. So we're going to break it down looking at basically odd and even patterns therein. So if we're moving from a negative odd number, which we'll call 1 minus 2L, to a positive even number 2L in the table, the generation index decreases by 1. So this one's quite simple to see if we just draw a little sketch. If we start with any integer L, 2L is in the next row by doubling. And then if we do double and then 1 minus 2L appears in the generation beyond that. So if we're starting with a negative odd number, such as 1 minus 2L in the table, moving to the next positive even number, we're actually going backwards 1 generation in the tree. So we go back to the table, you can see that here. If we're going from, say, -1 to +2, the generation index goes from 3 to 2. If we're going from -3 to +4, the generation index goes from 4 to 3, and so on. So it's always decreasing by 1. So that's the first pattern. And we'll go through a series of these, sort of relating what we get when we move from one term to the next in the table. So when we're moving from a negative even number, such as this -2, to a positive odd number, 3, in all of these instances, the generation index increases by 1. And we can prove these things based on the operations and how they work. So a couple more. If we're now going from a positive odd number, which is greater than or equal to 3, to its negative, we have 2 cases. So if k is equal to 1 mod 4, the generation index increases, such as if we go from 5 to -5. If k is 3 mod 4, such as right here, we're going from 3 to -3, it decreases by 1. So we have this sort of alternating pattern of increase, decrease for the odd integers. What else? So now if we look at the even numbers, so we're going to split this into 2 cases. If we first look at even numbers that are not powers of 2, so if we write these numbers as 2 to the j times some odd part m, where m is greater than or equal to 3, the behavior depends on the value of that odd part m mod 3. So if m is equal to 1 mod 3, it increases by 1. If it's, 1 mod 4, it increases by 1. 3 mod 4 decreases by 1. So again, some examples here. The first instance would be k equals 6. It has odd part 3, which means that 3 mod 4, we're decreasing by 1. Or here, m is 5. If we're looking at k equals 10, the odd part is 5, and it's increasing by 1. So we have another sort of alternating pattern there with the even numbers. And one more, lastly, something kind of interesting happens with the powers of 2. So if we look at the powers of 2 in the table, including 1, so 2 to the j, where j is greater than or equal to 0, the index always jumps by 2. So from 1 to 3, 2 to 4, 3 to 5, and so on. So we've pretty much completely characterized what's happening in the sequence in a recursive way. So at least, we can keep writing out the sequence based on these patterns without going back to the tree or thinking about the operations anymore. However, it would be nice to sort of get a better grasp on this sequence. What's happening? Is there some kind of formula for it that's not recursive? So that's part 2 of the talk, which is where we're going to find an expression for this sequence, this generation index. So we're going to redefine a couple of things here. So instead of using I as the generation index, we're going to use a sequence, we're going to index it using a function fn. So instead of counting k equals, instead of counting k equals 0, 1, -1, 2, -2, we're just going to let those count up from 0, 1, 2, 3, 4, 5. We'll define that as n, and then f of n is going to be that sequence we're interested in, i.e. The generation that k is found in. So we can see n and k are related this way. So for negative values of k, they give us even values of n, positive values of k give us odd values of n. So just to understand what's going on, a quick example, for k equals -5, that corresponds to n equals 10, and then f of 10 is 7, which tells us that -5 appears in the 7th generation. So just redefining that as a function f of n. So what are we going to do next to sort of try to get a handle on what's happening here? So one thought we had was to look at the difference sequence, which we'll call f sub d, and we'll define fd of 0 to be 0, and then we'll look at the difference sequence of fn. So here it is here. This time we're reading column-wise, and basically you can see that these are just the jumps in the indices we looked at before. We saw there was a lot of increase by 1, decrease by 1, and then occasionally when it lined up with the powers of 2, we had a jump of 2. So basically we're just looking at the change here from one integer to the next. So of course we ran to OEIS. Is the difference sequence in here? No, it wasn't. And again, it's there now since this work was published, but it wasn't there at the time. So this sequence wasn't in OEIS. We still don't really know anything about it. However, some similar sequences were in OEIS. So we thought, well, this is a nice sequence made up of mostly 2 characters, 1 and -1, but we have some extra 2s in there. So we thought, well, what happens that, okay, we know for when n is a power of 2, f sub d of n is 2. What if we just get rid of the 2s? So we're going to modify the sequence by dividing out the 2s, and we're going to denote this new sequence by a sub d of n. So it's kind of the analogous difference sequence where we get rid of the 2s. So meaning anytime n is a power of 2, we divide it by 2. If it's not a power of 2, it stays the same. And then we get this sequence. So apart from the 0, right, everything is 1 or -1. Okay, checked OEIS again. This time it was there. So we landed on something known, which was exciting. So what was the sequence? It turned out to be a Jacobi symbol. And OEIS also told us that it followed this recursion here that you can see. And we were able to verify that our sequence is actually matching that sequence in OEIS because we were able to prove this recurrence based on those sort of 5 patterns we uncovered earlier. We were able to sort of recover this recurrence. So we were able to prove that these sequences were indeed the same. So still, that didn't really get us anywhere. It gave us a nice new recurrence, but we want to sort of come up with a non-recursive way to describe this sequence. So we tried one more thing. Instead of looking at the sequence of negative ones and ones, and I think this might have come from OEIS anyway, if we replaced all the negative ones by zeros to instead get a binary sequence, this is also a known sequence. This is the regular paper folding sequence, also known as the dragon curve sequence. So lots known about this sequence. So this is looking good. At least we're getting into some known territory. So just to recap, we started with the sequence Fn that told us which generation our particular integer occurs in. We looked at the different sequence that we called F sub d. We divided out powers of 2 to get A sub d. And now the idea is, let's look at taking partial sums. We're kind of going back in the direction we came. So we started with a sequence, looked at the different sequence, divided out the 2's. Now we want to go back and take the partial sums of the sequence A sub d. So here is A sub d, our sequence of 1s and minus 1s. If we take the partial sums of this sequence, we get a new sequence that we're going to call AN. And this is really analogous to the sequence we started with, but remember, it's a little bit different because we divided out those 2's along the way, but we're getting closer. And this sequence, the partial sums of this sequence with 1s and negatives 1s, also was an OEIS, which was very exciting. So what is this sequence? It counts numerous things, but one of them is that it counts the number of runs in the binary expansion of n. Also, it counts the number of ones in the gray code of n, which is related to binary. So this was exciting because now we have a sequence very similar to the one we started with, and we're able to calculate it in an easy and non-recursive way. So just to recap, k are the integers, and this is just an ordering for a function. An is the sequence that we're studying now, and then it's the number of runs in the binary expansion, meaning the number of groupings of 0 and 1. So if we look at, say, n equals 6, in binary it's 1, 1, 0, we have a group of 1s and then a 0, so there's 2 runs. 1, 0, 0, 1, we have a 1, some zeros, a 1 again, so that's 3 runs. When n is 10, we get 1, 0, 1, 0, so that's 4 runs. So this is something that's easy to calculate, easy to program, which is what we wanted. So we just need to get back to that function f. So remember, the difference is that we divided out those powers of 2, so we want to put them back in. So ultimately, our original sequence Fn is equal to An, which is counting these binary runs, plus the floor of log base 2 of n. Okay, putting back in those 2's that we divided out essentially. And now still, this is something that's nice and easy to calculate. And again, just recall that this gives us the generation index for any integer k, where n and k are related in this way. So just to sort of put everything together, again, we have our k and our n, a of n, the number of binary runs, plus this floor function. And remember, if we add column 3 to column 4, that gets us back to our original function fn, which we were interested in studying. Now we have a nice, easy way to calculate this that's non-recursive. So what do we do with it? Well, let's go back, try to apply this to the original problem. Now, I guess this is kind of a spoiler alert because we were looking at this open problem, and now this is the counterexample. So there is a counterexample that we'll see. So remember, we're interested in which generations contain a Fibonacci number or it's negative. So we only really care about where the Fibonacci numbers occur. We don't care about everything in between, which is why recursive formula was really, too much work, too much computation. So if we restrict ourselves to these specific values only, here's a table for the first 64 Fibonacci numbers and their negatives, and it tells us the generation index. So you can see we're starting with 1, 1, 2, 3, 5, 8, and the negatives, and we're reading across the rows. So the next row would be the location of 13, negative 13, 21, negative 21, and so on. So here we can see the location for the first 64 Fibonacci numbers and their negatives. So remember, the whole question was, does every generation contain a Fibonacci number? So what we want to do is look and see, are there any generations missing from this table? So it might take a few minutes if you were to look through this, but if you started counting, looking for all the integers, you would notice that 43 is the first one that doesn't appear in this table. And this does jump around a bit. So we have 40, 42, 41, 45, goes down to 34, and then up to 50 and down to 44. But at least as far as this table goes, I mean, it's generally increasing, but going up and down a little bit. 43 doesn't appear in this table. So that's a potential candidate. Other numbers missing from the table, 47, 53, 61, 66. So it seems that these generations, right, generation 43, may not contain a Fibonacci number or it's negative. But we can't be so sure because we only calculated up to the generations for the first 64 Fibonacci numbers, and we don't know what's going to happen if we kept calculating that table. Okay, so we're going to look at proving that 43, generation 43, does not contain a Fibonacci number or it's negative. And it's pretty simple to see. If we go back to the original formula, we have A of n plus the floor of log 2n. Now, AN was that sequence that's counting the binary runs. It's going up and down a little bit. So it's neither increasing nor decreasing, but at least this log function is non-decreasing. So it's not a good lower bound at all, but it does provide a lower bound, and it's sufficient for our purposes. So we know that f of n is greater than or equal to the floor of this log function. So what do we do with that? Well, remember we had calculated for the first 64 Fibonacci numbers and their negatives. So what is the 64th Fibonacci number? You can see here, I won't even try to say it, it's gigantic. And then the corresponding n is roughly double that. So if we take the floor of log base 2 of this number n, we get 44. So that is the lower bound in this case. So if we go back to the previous table, we saw that of the first 64 Fibonacci numbers and their negatives, none of them occurred in generation 43. But now this lower bound tells us that that generation has to be greater than or equal to 44, right? So really this means for any Fibonacci number past the 64th, it has to occur in generation 44 or higher, which really means that because 43 hadn't appeared anywhere on the table, we've surpassed that lower bound. It's never going to appear if we calculate it further. So some of the other numbers like 47, and I forget what the other ones were, 51 or 60 something, we'd have to kind of do the same thing and calculate a little further to make sure that they are not going to later show up by finding a similar lower bound. So at least we've proven in this case that 43, generation 43 will not contain a Fibonacci number or it's negative. So that's a proven counterexample to the conjecture that was proposed. So a few more notes. We look at generation 43, the 43rd Fibonacci number is 433 million. So of course we were never going to find, we would have had to calculate a tree that had 433 million entries in that generation. We never would have found it by hand, of course, and even computationally, we weren't able to find it by brute force. Sort of a side note, but there's another nice recurrence that we found, which is nice, but again, it's really cumbersome to use because we don't want to calculate this recursively. We're actually only interested in the Fibonacci numbers and not everything in between. So just to finish up, we might want to ask then, well, if we found one counterexample, how often do counterexamples occur, right? How many generations fail to have this property? So the first several are listed here, and there's a lot of them, so it's not entirely unusual. It just so happened that it seemed like a nice conjecture because we got so far up to generation 43 without finding any Fibonacci numbers. But in the end, it seems like maybe there really isn't anything special, of course, about the Fibonacci numbers and where they occur in this tree. It just so happened that we didn't find one for so long. So if we kept calculating up to the first 5,000 Fibonacci numbers, they occur within the first 3,741 generations. Of those, 509, or roughly 14.66%, did not contain a Fibonacci number or it's negative. And if we compute a little further, again, we're seeing between like 14.5 and 15% seemed like they didn't contain a Fibonacci number. So we didn't really go too deep into this yet. These were just some sort of early calculations. And we also did this for generalized Fibonacci sequences where we're starting with terms 1 and A, where A is an integer between 1 and 12. And again, calculating a little further in the tree, it seems that between 13 and 15% of generations, again, fail to contain a number in the sequence. So it turned out that maybe the original question wasn't all that interesting once we found a counterexample, because maybe there was no real connection between the Fibonacci numbers and this tree. But I think the interesting thing that did come out is just this tree and the structure of the tree and how it tied into some interesting known sequences like the dragon curve sequence, and how this kind of interesting two operations partition the integers into the generations in this way. So that's the end. Thank you for your attention.
Thank you very much. Are there questions for Karyn? We have a few minutes. I always like to wait a second because people type into the
Yes.
Q&A. But it seems that there are no questions. So let me thank you again for a very nice talk. And we have a 4-minute break.
Great,
Thank you.
thank you.